Now let us see what Krushkal algorithm looks like. This is an algorithm for Krushkals. Name of an algorithm, Krushkals. Input, a weighted connected graph G of V comma E, where V is set of vertices and E is set of edges. Output a set of edges that will be constructing minimum spanning tree. ET, it is set of edges. And next, we sort all the edges as we have seen in the previous example. To begin with our Krushkal's algorithm, the first thing we do is we draw a edge table wherein we arrange all the edges in ascending order. That is, sort all the edges in ascending order. Same thing, sort all edges of E in non-decreasing order. That is ascending order. That is weight, whereas that is weight of first edge that we have written is lesser than the second edge that we have taken. Second edge is lesser than the next edge, and so on. In this way, we arrange all the edges in an ascending order. Initially, the set of edges in our spanning tree is null, that is, there are no edges, so it is initialized to null. ET is equal to null or 5. And the next statement, encounter is equal to 0. Encounter is a variable that will keep track of number of edges that we have added up in spanning tree. So the number of edges that we have added up in ET. So initially we have no edges in our spanning tree. So that is why it is equal to 0. And the next statement where k is equal to 0, it is just an index to move from one edge to another edge. So since we have all the edges in a array form, we have to choose the one edge which is smallest. We do not choose this in sequence wise. So that is why we need an index for choosing an edge. So that index is k. Initially it is 0 because we have not yet chosen anything. Now we begin our algorithm while loop with a while loop. While encounter is less than v minus 1. V modulus is equals to number of vertices minus 1. As we said, in a spanning tree without cycle, it will always have n minus 1 number of edges if it has n number of vertices. For n number of vertices, we always have n minus 1 number of edges. So to make sure that we do not have cycles, we have taken this statement. Encounter, that is number of edges in your spanning tree, should be lesser than the number of vertices minus 1 of your graph, main graph. So within a while loop, we have, that is the first edge we choose from our edge table. So that is why k is equal to k plus 1. That is, we are using an index of k, we choose one edge from our table. K is equal to k plus 1. That is, one edge has been selected. If ET union EK is acyclic, that is, initially the set of edges in your spanning tree is null. So if I add up this edge that I have newly chosen, if it forms a cycle, that is, it is a cycle. If it doesn't form a cycle, then you add up this edge into your ET. That is, you add up this new edge into your spanning tree. Else, you discard it. So that is why when you choose a first edge, you check the condition whether adding up this edge into your spanning tree or ET, will it create a cycle. If it doesn't create a cycle, you add this new edge into your spanning tree. That is, ET is equal to ET union EK. EK is a new edge that has been chosen. So after you add up this edge into your spanning tree, now you start counting your number of edges in your ET. That is your spanning tree. That is why E count is equal to E count plus 1. Initially, in count was 0 because we didn't have any edges. Plus 1. We have added up one edge EK in our ET, that is spanning tree. So that is why we have one edge. So again we move on to the next. Your I will be incremented, that is your loop will start looping again. So the next edge is chosen, EK, another edge. Now check adding up this new edge, will it form a cycle? If it doesn't form a cycle, you add it into your spanning tree. If it is creating a cycle, you discard it, move on to the next one. In this way, using a while loop, you encounter all the edges that are present in your edge table and see whether they form a cycle or not. If they do not form a cycle, you add it into your spanning tree or else you discard it, making sure that the number of edges that you encounter should be lesser than the number of edges, so should be lesser than the number of vertices minus 1 in your main graph. So this is how your algorithm looks like. And the efficiency, total efficiency taken by this algorithm is big O of E log E. E is number of edges in your graph. So E log E. So here we have an example. So let us take this graph. So this is our graph. So using Krushkal's algorithm, we are supposed to form a spanning tree. So we'll draw, first step, we have to draw an edge table where we have all the edges sorted in ascending order with respect to their weights. So we have A, B, B, C, B, D, A, D, D, E, C, E, C, D. 7 number of edges. So let us all arrange it in your non-decreasing order of your edges. So BC 1, DE 2, BD is 3, DC is 4, AB is 5, AD is 6, and CE is 6. So actually it should not be written in this way. It should be written in an edge table as I've shown in the previous example. So you better choose that way. So we'll start our algorithm, that is drawing an algorithm, implementing our algorithm, finding out a spanning tree. So the tree edge that we have to choose from your edge set or edge table is first edge, that is BC. The tree edge that I select is BC. Does it form a cycle? That is whether it is acyclic or cyclic. It is acyclic. So you add it in your spanning tree. Next edge that I choose is DE. DE. Whether adding up this edge DE will form a cycle. Is it acyclic or cyclic? If it is cyclic, I would have discarded it. Since it is acyclic, I add it in my spanning tree. The next edge is BT. I choose BD. Adding up into my spanning tree will not form a cycle, so I have kept it. Next to DC. If I join DC, I'll form a cycle like BCD. It will form a cycle or a circuit. So that is why I discarded. Move on to the next next edge, AB. It is acyclic. I have only B, C, D, E. I don't have A. Even if I have an edge between A and B, it will not form a cycle. So this is my next edge into my spanning tree. The next, see, look at the vertices. I have 1, 2, 3, 4, 5. So number of edges that we should have in our spanning tree is 5 minus 1, that is 4 edges. So have we encountered 4 edges? Yes. So this is an indication that our spanning tree is completed. But still, if there are any edges, you can still try and find out that it will form a cycle when you add up some more edges. So the next edge is AD. If I add up AD, I'll form a cycle. So it is discarded. The next edge is CE, which again will form a cycle if I add it in my spanning tree. So now I have a spanning tree with the cost of 11. So this is how we have to solve spanning tree using Krushkal's algorithm. So let us see the differences between Krushkal's algorithm and Prim's algorithm. So Krushkal's algorithm, as we have seen, we always try to find the smallest or the minimum edge in our network. Whereas in a Prim's algorithm, we look for a vertex which is nearer for the next adjacent vertex. This is different. The second difference is the next shortest edge which does not create a cycle. Here we look for a next edge that is connected to the vertex that we already have in our tree. We cannot add up any edge which contains the vertices which are not in a tree. So we have seen in Prim's algorithm, when we have an edge between U and V, we always see that one of the vertex, either V or U, is in our spanning tree or spanning tree edges. The other one is not in my spanning tree edge. It is in your main graph. But whereas in Krushkal's algorithm, there is nothing to do with the vertices. We always see the edges which can be added up to our spanning tree, and no cycles are formed. Of course, in both the algorithms, we check if it is forming a cycle or not. Any edges that we have chosen. If it is forming a cycle, we discard it and go for the next one. So this is how your Krushkal's algorithm and Prim's algorithm differ in functioning. So here I have an example. So the same given graph, if we apply Prim's algorithm, this is the first graph what we have on the topmost. That is a result of Prim's algorithm spanning tree. Whereas the second one what we have, it is a result of Krushkal's algorithm. How does it differ? So let me show an example. Taking if I apply Prim's algorithm for this given network. How does it work? We take one vertex as a root vertex. So I begin my root vertex 1. Then I choose the shortest vertex from this one. So among this vertex, which is the smallest one, 2 is the smallest vertex. So I'll take that one 2. Next, choose the next nearest vertex, which is not in my solution. I'll take another 2. Next 3. And then 4. And then 3. So adding up some more vertices, some more edges to my spanning tree will form a cycle. So I stop here. So when you look in every step, I was actually trying to find out the next nearest vertex to the vertex that I've already have in my tree. I was not looking for any random edge to my tree. So this is how your Prim's algorithm works. Whereas your Krushkal's algorithm, for the same graph, it looks something like this. I choose the first smallest weighted edge, that is 2, the next smallest edge, that is again 2, and the next smallest edge is here 3. So if you notice, in my spanning tree earlier in the third table, in the third box, I had only these 3 vertices. But in the next step, I choose 2 different new vertices into my spanning tree. This will violate in my Prim's algorithm. In my Prim's algorithm, I'm only supposed to find out the vertex, next nearest vertex to the vertex that I already have in my tree. Look at the box 4 and 5. Here in 5, I choose the next nearest vertex to here for 2 third. But here, I choose the next nearest or the smallest weighted edge. So that is why the same graph, when it been applied Prim's and Krushkal, it will gain 2 different kinds of spanning tree. So this is how your Krushkal's algorithm and Prim's algorithm works. I hope you have understood. Try to solve the problems using the same method.